Okay, so find the equation of the line that's tangent to this graph and parallel to this line. Now there's a lot of algebra we need to know in here. One of the pieces of information that we need to know is, what do you need in order to write, and I don't know why my pen is has this delay, so I'll have to write slow, and hopefully you'll be able to read it. But what do you need in order to write the equation of a line? You need the slope. There's only one. You need the slope, okay? And you need what? To write the equation of a line. You need something else. That is very, very specific. That's too specific. Be more general. A point. Yeah, a point. Now, you can have the specific point, which is the output intercept, but it doesn't have to be that specific point. Okay. So we need that information in order to write the line that we want. We need to be parallel to a line. So what does this bit of information tell us? Two lines are parallel if slopes are the same. Okay, so we can find the slope, so we can determine the slope from here. Okay, we can determine our slope from here. How do we do that? So go ahead and use this information. What I'd like to have you do is on your Inspires, just type in fact, I'm going to send you a quick poll, and I want you to find the slope of that line. And I'll correct this here. Again, some little participation points come when I do this. Yes. Can you what? Reset your password. Not until I get done with this. Okay? We'll have to finish this up first. So I'll look for 5 more people here. This is a case where I don't know is not appropriate. Everyone should know how to find the slope of that line. 3 more people. Logging in quickly, please. Or submitting an answer. Okay. 1 more person, and then we're going to stop this. There we go. Okay, so let's just take a look at this. The slope. Now, the slope cannot be 3x cubed minus y. I assume that's what this person meant. The slope is not an equation of a line. The slope is a value. Okay? The slope. The slope is the inclination of the line. The slope is 3. So we have that's correct, this correct. -3, no. -4/3, no. Again, the slope is not an equation of a line. The slope is a single value. So we'll save that to the portfolio for today. And let's go back. Excuse me 1 minute while I reset your password. Go ahead and give it any 3-digit number now. Okay. So we know then that the slope is 3. With that information, find the equation of the line as tangent to this graph. We need a point of tangency, correct? If we're going to be tangent to that graph, we need a point of tangency. We know the slope. How does the slope fit into the work we're doing in this whole course? The fact that this line is slope 3 tells us that the line we want also has slope 3. But how does knowing the slope or finding the slope or determining the slope, how does that fit into what we're doing in this course? Last time I was with you, in your notes you should have that there are three major topics we talk about. One's a limit. Yeah. Derivative. Okay, what is a derivative?
Slope.
Oh, think about what you just said. The slope of a point.
The slope of a line.
Okay. The slope of a line. Okay, so the derivative is the slope of a line tangent to the curve at a point. Where did I write that down for you guys? Somewhere in my notes, and you should have it in your notes also. And it may have been in the video notes. There we go. What is it? The slope of a line tangent to a curve at a point. Everyone needs to know what that is. If we don't know what a derivative is, we're lost. We're just memorizing a bunch of junk. That's what it is. Just a bunch of junk. I don't want you to do that. Life's too precious. We don't want to waste our time. So the fact that I know what the slope is, though, if I didn't know the slope, let's go with that. If I didn't know the slope, how would I find the slope? We want a tangent to this curve. Now it's Joe. Joe just told us that the derivative gives us the slope of a line tangent to a curve. Come on, everyone now should be thinking, hopefully, that if I didn't know what the slope was, I could find it by taking what? Or finding what? The derivative. How do I find the derivative? What's our process? Someone needs to help me out here. The derivative is, according to this section, not in this section. And by the way, that's not what a derivative is. The derivative is not moving that number around and all that stuff. That's the process. That's a shortcut. We get that in section 2.2. Hang on, okay? But when you know what the derivative is, how do we use all that work of section 1.5, limits, to explain what a derivative is? Give me more information. The derivative is the slope of a line tangent to a curve at a point. How do you find a tangent to a curve? Let's take the inspires right now. Take the inspires, add a new, go home. If you want to, do you want to save? Say no. Pick up a, let's just jump to a graph page. And I want you to type in x cubed plus 2. Let's do something else. When you have that tab, and that brings up that entry line again, let's put in that equation of the line that's parallel to our tangent line. Now, in order to do that, it's going to have to be in what form? Not 3x minus y minus 4 equals 0, but in what form? Okay, do you have that on your notes? Okay, so it should match mine, 3x minus 4. There's the line, okay? Now, our line, this line is going to be tangent to, or excuse me, parallel to a tangent line. Let's see if I can do this. If I pick up this line and I move it, can I make it tangent? I changed the equation, but I can make it tangent to that. And how many places, let's look at this, how many places do you think this line is going to be tangent to the curve? There's one. Is there another? Can this line be tangent to that curve at another point? There's one. What do I have to do? What quadrant's it going to be tangent in? Second one, yeah, right there. So we got 2 points of tangency on this curve. 2 points. We got to keep that in mind. Okay, so I'm going to go back here and put that back to 4, where it was before. Okay, and we now need to find this point on the curve. We can come up with the fact that it's going to have slope of 3. We know that, but we got to find that point. Now, when I look for that point of tangency, remember we can get a line that's a secant that kind of cuts across it, but we're going to want to move it so that the slope of the secant line becomes the tangent line then. And so we're going to look at this, and let's just fill this in, make sure this is part of what I'm going to be testing you on in, what is it, 2 weeks? Not next Tuesday, but 2 weeks from today. You need to know this. You need to know this. The derivative is the limit as delta x approaches 0. What does delta x stand for? My pen has never acted this weird except this semester. Last semester it was smooth as could be. So I don't know what driver. I just loaded a new driver and it didn't seem to be helping any. Okay, so again, delta x stands for what? Okay, so that's the change between the 2 points. One of the point is the point of tangency. And we are looking at basically what am I going to write here? An expression for what? This fraction is really an expression for what? This fraction is nothing more than an expression for what? Slope. 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 You know, I think we've lost a lot, and you know, I don't buy the fact that I've not been in front of you, that's the reason why you guys aren't, you know, answering my questions and you're not learning. My video lectures are just as if I'm here. But I have a feeling that because I'm doing video lectures, maybe you're not paying as much attention to them. Please, please, please. You've got to pay attention to those video lectures. We did stuff like this. We went here. I'm going to put a couple of points on here. Put a point there. Put a point there. Okay. I'm going to, and you don't have to follow me. I'm just going to demonstrate here. I'm going to put a line through this one and through this one. I'm going to measure the slope of this line, and the slope is 1.61. Okay? That's the slope of the secant. So let me go in here, make sure that we understand this. The slope of that secant is 1.61. Now, I don't want the slope of that secant. I want the slope of a line tangent to this point. So what happens to this point? I move it. What's happening to the values of the difference of my inputs as I go from here to here? The difference of my inputs is what? As I go from here to here, what's happening to the difference, the subtraction between the input values? Becomes almost what? 0. Isn't that what this is saying? It becomes almost 0. That's the idea behind all of this. Okay, so as I bring this closer and closer, and let me just do one window here, make sure I can get a better window on this. We'll go, there we go. There's that point. There's the equation of our line and so forth. Okay, so Whoops, what happened to my, there it is. Okay, so as I bring this closer and closer, the input values are difference between those are getting to 0. What's happening to the slope of that secant line? It should become 3. Okay, now why isn't it becoming 3? Maybe that's not the point of tangency, right? Maybe that's not the point of tangency. So I'd have to move this point to a different place. Let's see if I can get it to be almost 3. It's a guessing game at this point. But what am I looking at? What am I considering it? I want the slope of the secant to become what? 3. How about doing this? What does this fraction represent? Slope. Don't forget it. Okay, so that fraction becomes slope. How do I write the slope in the derivative fashion? F of what? Okay, so I get the output of the new point of 1 point minus output of another point, and I subtract the inputs. And what does that become down here? Delta x. Okay. Now, for us, we've got the limit as delta x goes to 0. And I now need to interpret what is f of x plus delta x. In your Inspires, I'm going to send you another quick poll. I want you to type in only f of x plus delta x. And I can't do the symbol here, so I'm going to have to type it out. Delta x. That's all I want is just that expression with x plus delta x. All I want to know is how do you interpret f of x plus delta x? Don't go any farther than that. We may never move from section 2.1. We may never get to that shortcut. Because I need to have confidence that you guys know what it really is. Yeah. It won't send? Did you tab down to the send and press enter? Pardon? Bring it up and let me see. I've got 10 of you in here, so I don't know why 2 of you. Maybe you've already sent it and didn't realize it. You might have already sent. Okay. Although usually it goes away, doesn't it? Let me ask that again. When you send it, does it usually go away? Yeah. Okay. Okay. 2 more people. You have the same problem, Joe?
Yeah.
Okay. Try it one more time. I'm going to watch the counter here. 13. Okay, did you just send it? Yeah, I know. I don't know why. Okay. Okay, well, we'll assume that everyone has that. Let's take a look at this. No, I gave you f of x plus delta x, but I didn't want the f there. What's the 3? 3 is the slope. 3 is the result of taking the limit as delta x goes to 0 of that slope. So we don't want the 3 in there. Well, I know it's the limit, but it's not truly the limit. I asked you to do a portion of that fraction, so it's not the limit. X cubed plus 2 plus delta x. I don't think that would be correct on that. No, I gave you that. You can't give it back to me, okay? This is the problem. If we don't know what that is, we have a huge, huge problem. Now, I like this. Take a look at this one. When I ask you for f of, what is that quantity inside the parentheses? Input or output? Input. What do you do with an input value in a function? You go to the function, you find everywhere where the input variable is, and you do what? Substitute it. Yeah. So everywhere you see the input variable in the function, you need to substitute what into it? X plus delta x. So there you go. This is the first correct answer I have. Okay. Why did we change it to A? Is that the delta x feature? Is that someone's idea? Yeah. Is it? Okay. Okay, just need to know that. Okay. Because when I stop this and save it to the portfolio, I can give you guys points on these answers. Okay? And when I give you points, I want to make sure okay. I want to make sure that I have that. Okay, so I'm going to update, and I just did that. So let's take a look at that. And let's continue on here. Everywhere, this is the input. Everywhere I see the input variable, I'm going to have to put in x plus delta x plus 2. And I'm going to put this in brackets to remind myself and you that in fact is f of x plus delta. That's this whole quantity right here. Now, continuing on, I need now to put in f of x. Well, f of x is x cubed plus 2 divided by delta x. We're back now into section 1.5. Are you ready for the quiz Thursday on section 1.5 and 1.6? I will give you things like this. This is that you don't need to interpret it as slope. You just need to know how to finish it up from here. Now, there's a couple of things you can do. And by the way, we never drop the instructions of taking the limit until we do what? Direct substitution. Okay, when I can make direct substitution and I can put 0 in for delta x and it does not make it undefined, I'm as happy as can be because I'm able now to take the derivative. I can't substitute 0 in because I get a 0 denominator. Now, what is the cube of a binomial? I happen to know by heart. You may not. I'm not going to ask you to do it by heart here. Let me just see if this helps at all. But if you take your inspires, you see that circle? I'm not sure what that circle's on. Okay, well, whatever. Take your inspires. There's something else working on my computer, and I'm not sure. What an awful thing you have to look at. But take your inspires, and I want you to, let's just go home and pick up a calculation page. Go to menu, go to algebra. You see this thing called expand. And when you expand, it means things like this. Let's type in an x plus, now instead of delta x. You won't be able to put in delta x. Let's substitute h. H is one of the things that you'll see in some textbooks for this. So let's put an h in here, or an a, or whatever you want, and move outside of that, and let's raise this to the third power. This is the power of a cast system. This is why you bought these or are using these. Because, yep, well, it should work there. Let me get back up here. I've got an extra set of parentheses that I don't need. So let's do this. There we go. And I'm going to, I'm just going to erase that and start all over again, you guys. Okay, I forgot to put the parentheses in side. Now I'm having troubles here, so we'll just do that. There we go. Expand came with its own set of parentheses, and so let's see now. There we go. That's what it should be. It came with its own set of parentheses, so you have to put everything inside that parenthesis that came up. So we've got x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed. Okay, so let me expand that here. So I have x cubed plus, then there's a pattern to this, but I won't take our time to do that. X squared delta x plus 3x delta x squared plus delta x cubed. And then we have the plus 2 on the end. Minus f of x. We still have that. Now I'm just going to go ahead and write that as x cubed. Remember, you were distributing that negative. X cubed minus 2. If you didn't distribute that, you're not going to get the right answer. Okay, once we have this expanded, everything's out there as single terms, added or subtracted or whatever, we then look for items that we can cancel. And when we look for those items to cancel, we must be able to cancel every term that does not have delta x in it. Why must every term that doesn't have delta x in it be canceled out at this point? What's the next step? Why is it important that only thing left are terms with delta x? Yeah, it's the delta x in the denominator that's our problem, okay? Now, every term in the numerator has a delta x. We can factor one out. Okay, so here we go. The limit as delta x approaches 0. And if I factor out a delta x in that numerator, I'm going to have 3x squared plus 3x, we can see that, delta x plus delta x squared, let me overemphasize that, divided by delta x. It is important that everything in that numerator now have a delta x in it. It is the only way that now I can cancel out the problem. Now can I use direct substitution? Yeah, and my answer is 3x squared. Matthew, did that come up to be what you thought it was going to be? Absolutely. But why does that work? Because of this, okay? Now, we spent a lot of time just getting the derivative. Just getting the derivative. So what? So what? I got an expression for the derivative. That's another function. Another function. We call it f prime of x. Another function. But what do we know is the output of this function? What's the output we want this function to have? Who said it? And you said what? How do you know you want 3? And because the derivative is the slope of a line tangent to a curve, it makes sense then. We want this expression now. This is an output. We want, okay, we want the slope of the tangent to equal 3, and that's the same thing as the derivative, which is the same. By the way, what do equal signs tell you? Very basic. But what are those two parallel lines that we write as equal signs tell you? What? Where? Same value where? On either side of it, yeah. So if I have that the derivative is 3x squared, if I know that the slope of the tangent is going to be 3, and I know that the slope of the tangent is the same thing as the derivative, then I know that if it's called the transitive property. You know, if A equals B and B equals C, what do you know about A and C? Gotta be equal. It's called the transitive property. Okay, so if I know that all of this is true, then what? What now can I determine? Three equals 3x squared. What can I determine? Well, that's an equation, right? What do you do with equations that have an unknown in them? Solve them. Solve them, yeah. Can you solve this equation? X equals what? Yeah, positive 1 or negative 1. Okay? Now, have we accomplished what we set out to do? Did we answer the question that we have here? Let's go back to the top. It said, write the equation of the line. Did we write the equation of the line? No. All we know at this point is that the slope is 3 and that the point is has either an input value of 1 or negative 1. What else do we need to know? We need a point, right? If the input is 1, what's the output? If x is 1, f of 1 is what? 3? Because 1 cubed plus 2 is 3. Okay. If x is negative 1, what's f of x? How much? I thought I heard someone say negative something. How much? You sure? Negative 1 cubed is negative 1. Negative 1 plus 2 is positive 1. Do we have points now? We have the point 1, 3, and we have the point negative 1, 1. Okay, go down here. If that's true, then the equation of the tangent line let's see, we've got y equals m the quantity x minus x1 plus y1. Where did this formula come from? Say it louder so I can hear you. So, where did it come from? You're actually correct. But you know, it's a little easier than that. Let me put it over here. I don't know if you can see green on this board or not. Maybe you can. What did you learn back in Algebra 1? Slope is what? Kind of like this. what happens when you multiply both sides by this denominator? You get m, the quantity x minus x1, right? Equals y minus y1. What happens when you add y1 to both sides? That's what this comes from, okay? This is nothing more than a variation on the slope formula. So there's no reason to memorize it. If you know slope, you know how to get to this. So here we go. Let's find the let's find this. So for the point m equals 3, and the point, what was that, 1 and 3, our line is going to be 3, the quantity x minus 1 plus 3. And I expect you to simplify that. There's no reason to leave it like that. 3x. Okay. And for the slope of 3 and the point negative 1, 1, we have y equals 3, the quantity x minus a negative 1. Don't forget, that's going to make that a plus 1, or simply 3x, and then what? Careful. Okay, let's check and see. If we are correct on this, if we are correct, I know that this point has to be what? What did we say the first one was? I forget, you tell me. 1, okay. And that puts it right up there. I'm going to take that line away. Let's see. There we go. Take that line away, and let's make this one at negative 1. Okay. Now let's put some tangent lines on there. Put a tangent line right there, and I'll put a tangent line right there. Don't forget that if you grab the ends of the arrows, you can extend those so you can see them easier. Now, on the test, on the quiz, and then on the test, I'm going to ask you probably to do what I always do, and that is show me some graph work that proves to me you understand this. I would expect you to do something like this. But what's missing? What do you need to show me now? What makes these lines correct? The slope. The slope has to be 3. And we hope that if we look at the equations, they match what we just wrote. Let's try it and see. Go to menu. Go to actions. Whoops, let's try that again. Go to menu. Go to actions. There we go. And if you go to actions, you get this thing called coordinates and equations. Coordinates and equations. If I point to that line, and then I point to this line, and your work verifies what I see here, do you think I know that you know what you're doing and understand the whole math behind this? You betcha. Okay? Now, do you have to do this on the Inspire? No, you don't. You can do everything on paper if you want. But if you do it on Inspire, you can leave it on the Inspire, and then I can pick up your TNS file like I did on the quiz, and I can grade it from here, which I did on the last quiz. Okay? So don't feel intimidated by this piece of technology. It's only a little computer. That's all it is. But if you don't like to use it, I understand. But be able to do this graphically on paper and pencil then. Okay, any questions on this problem? Yeah, Joe.
Can you show us how you expanded
Oh, how I expanded the...
it's like
Sure. Let's go back to the Inspire. All I did was you go to menu, you go to algebra, and you go to expand. Okay, so be on the calculator page, menu, algebra, expand. Expanding, okay, the cubing of a binomial. Then again, remember, the parentheses comes with the command. So if I say this, I get a set of parentheses. If I'm going to cube a binomial, my mistake before was I didn't put another set of parentheses in there. Okay? And so if I do another set of parentheses, x plus h, move outside of that inside set, do my, cubing of it. And again, use something, don't try to use delta x to do this. Just put another letter in there, but then always go back and realize that you've got delta x in the problem. Your question? I think it is, I have to check my notes here and see, but it's coming up on a Tuesday. Okay? I've got some more traveling coming, okay? And so it's going to be slotted in there on a Tuesday between them. I'm not sure if it's next Tuesday or the week after that. I think it's the week after. I think it's 2 weeks from today. So I'll check it right now. I've got it for March 1st. Okay? I think that's it. Okay. Ready to move on? Good. Let's go on then. Now, what we just went over took much longer than it should have, to be honest. If you have been listening to those videos. Now, when I say listening to those videos, I don't mean just having them plugged in, your ear or on the, speakers here while you're talking to your friends or listening to other videos or talking. No. This is as if you're sitting here with me. So your attention is here. Your attention has to be on the videos. And when I get to a problem like that, you need to be working with me. Pause, try it for yourself, start it, continue, and just see if you can do those problems. And if you can't, you need to go back and do them again. So please do not just assume that because I'm not standing in front of you that you got a free ride this semester. I'm expecting as much out of you as I have always, okay? But you have to listen to those videos. Okay, the notation, we have looked at notation. We've used this one, that little prime mark. We are going to be using this one, and we say that it's dy dx. D is, and actually D stands for differential. It's not really delta at all, and I'll explain that later as we get into it. Dy dx, and at this point, don't think of that as a fraction, it's just notation. And then we also can use y prime. The others we don't really talk about too much. Now, I do want to point out, though, that this portion of this right here, what does that variable x represent, the input or the output? Input variable, or yeah, it's the input variable, okay? So we have to keep that in mind. And what does the y represent? And that would be our output. Now that becomes important to us as we move further into our semester here. But we have to keep in mind that that is the derivative of the input. Now, with that being said, take a look at this notation right here. Because we do use this one. I use it a lot. What is this piece? The x down here represents input again. What does this represent? Go ahead. What is it? The output. Yeah, the output. And so I can write things like this. The derivative with respect to x, that's the phrase that goes along with this. The derivative with an input variable of x of 3x squared plus 4. That's the same thing as asking for the derivative of the function f of x equals 3x squared plus 4. Determine the derivative. Okay? These are equivalent statements. I'm asking for the same thing here. Find the derivative of this output expression with respect to the input variable x. Okay. We will be seeing this many, many times over. Okay. Let's look at, let's look at this problem. Determine, given this, determine, and this is again the phrase, determine the derivative of y with respect to x. This is the same thing as saying determine the derivative with respect to x of the square root of x minus 1. These are saying the same thing. So I would want the slope of the tangent is the limit as delta x approaches 0 of, now we write the phrase out, we could also say this is f of x, if this helps, write it up here. This is the same thing as f of x, as we're going to say f of, same thing we've been doing, x plus delta x minus f of x divided by delta x. Same thing. So we're going to write the limit as delta x goes to 0. Again, take the input expression, x plus delta x, and everywhere in that function you see an input variable, you will make a substitution. So that's going to be the square root of x plus delta x minus 1. Make sure you enclose all of that in the square root sign, minus the square root of x minus 1. All of it divided by delta x. I've got a little rationalizing of the numerator. Some of you have an error on that quiz when it comes to rationalizing the numerator. Rationalizing the numerator means that you multiply by another fraction, not squaring the fraction. That doesn't do us any good at all. When I rationalize the numerator, I have to use what's known as the conjugate. The conjugate is exactly like this, except for what? The sign between these is different. Okay, so I've got the square root of, and I'm just going to write this as x plus delta x plus 1, or excuse me, minus 1, plus square root of x minus 1, divided by, now the problem is the original is over here. This is my original problem here. I've got to keep true to the original problem. The only thing I can multiply with any other value and stay true to the original value is what number? How much? 1. 1. Okay? It's called the unit, multiplicative unit here. It's the only thing you can multiply and stay true. So if I'm going to multiply the numerator by this, what do I have to multiply the denominator by? Same thing, yeah. Because this fraction over here is going to have an equivalent value of 1. Okay, so I've got now the limit, delta x approaches 0. If I multiply using the distributive property, the first term times the first term, they're identical. I'm squaring the square root, what happens? The reverse, so all I get is that radicand, so x plus delta x minus 1, okay? If I take the first term, we're just using distributive now, first term times the last, it's something completely different, okay? But if I take the second term times the first, what happens to multiplying the outside and the inside? They can't, it's like FOIL, you know, you've learned that little process, okay, they cancel out. So now I take the last term and multiply it to the last term. A negative times a positive is a negative. I'm multiplying a square root times a square root with the very same radicand, and there again, I end up with just x plus 1. Okay, denominator. Now this gets to be a little bit interesting because in my denominator, I'm going to have to keep this going. It's the square root of x plus delta x minus 1 plus the square root of x minus 1 what happens in my numerator? Yeah.
I have a second question. For the
Yeah.
numerator, is it x minus 1 or x plus 1?
Minus 1. Thank you. Thank you much. You know what? I would have found that out, wouldn't have I? Yeah, and that's the important thing. If you make a mistake, at this point, if you know where you're headed, you'll catch it. And I definitely would have caught it. So let's see, because this should be x plus delta x minus 1 minus x, and now it becomes plus 1. I know that it had to be what you said, because at this point, everything that doesn't have an x in it, or delta x in it, needs to cancel out. Now, if I look at this, the only thing left in my numerator is this delta x. What's preventing me from using direct substitution anyway? Oops. What's preventing me from using direct substitution? Can I get rid of it? And this is why it's important. There's that gone, and there's that gone. Okay. So now what I end up with is a 1 in the numerator. Can I use direct substitution now? Yes. Do I continue to write the limit notation? No. I have 1 divided by the square root of x plus 0 minus 1. I'll put those in just in case someone wants to see them there. Plus the square root of x minus 1, or simply 1 divided by 2 the square root of x minus 1. Okay. Did we answer the question? Did we find the derivative? It is another function, but there it is. Do we have rules that we can, shortcuts? Yeah, we do. We're going to figure those out. But we got to get through this section, make sure we understand what we're doing. We're looking at the slope of the secant becoming the slope of the tangent by moving those 2 points closer and closer together. Okay. Is it possible for a function to be continuous at a point, but not differentiable at that point? Now, you talked about continuity. We talked about it in section 1.6. A function is continuous if 3 things happen. What are those 3 things? We'll just do a little review here. Continuity. At a point if. What's the 1 criteria? Yeah. Okay, I'm going to go through a list here, okay? Because I see a sequence happening here. You're absolutely correct. It has something to do with limit, okay? Would this be considered continuous? Why not? Okay, f of c must exist, okay? And right now at c it doesn't. Well, what if I put this up here? Now does it exist? Yeah, it's up here at, we'll make this at B, and we'll make this down here at A, okay? So now, does the function exist at C? Yes, but is it still continuous? No, okay? So now, tell me what you were going to tell me. The limit as the input approaches what? C, okay? And it has to come from both sides. Okay, that's implied here. The limit of the function as x approaches c, what? There has to be one? Yeah, it has to exist. Okay, must exist. Okay. Now, I'm going to alter my picture just a little bit. And let's see, what do I want to do here? Oh, well, I won't alter it at all. Does the limit exist? As I approach c from both sides, what's the limit? The value a, right? The outputs are going here. So is it continuous? So far, I've got a yes for both of those. But what's the third criteria, and really the most important one here? They have to be the same. Yeah. So the output of the function at that has to be the same thing as the limit as we approach that point. And that's what fails on my example here. The limit is down here, but the actual value of the function is up here. So it's not continuous. Therefore, come on. Therefore, get another point. There we go. Therefore, f of x is not continuous at c. You know, my pen only seems to not work with this projector. I can't figure out what it is. Okay. Something with the resolution, I think, is messing it up. Okay. So let's go back now. Is it possible for a function to be continuous but not differentiable? We saw a function that wasn't continuous, okay, but is it possible? Now down here it says differentiability implies continuity. If it's differentiable, then it is continuous. If it is differentiable, then it is continuous. If we look at our example over here, if I'm going to look for a derivative, a tangent line going through here, I could look at tangent lines up to this point, but because there's no point here, I can't do a tangent at a point that doesn't exist. So this does not have a derivative at C. It's also not continuous there. Okay? So it's not differentiable, therefore, we have a statement, actually it's a theorem in another textbook. We have the statement that if it is differentiable, then we know it's continuous. But the question is, if it is continuous, is it always differentiable? And the answer to that question is no. And I'm going to, let's see, we'll look at some, let's see if this is the example I want here. Let me just give you an example. I'll draw them here for you. If we have, well, we'll just do the very simple, you recognize that as the absolute value function. What are the slopes? And we'll just assume it to be a simple one. What's the slope of this? The slope is negative something, right? We'll say -1 is the slope along here. The slope along here, We know it to be positive. And if this is my point C, is that function continuous? Let's see. Yeah, it's continuous. There's a value, there's an output value for this, and as I approach C from both sides, the output values are approaching the same thing. But is there a derivative? The derivative says that the slope of the secant, and we're going to have to assume this is the secant here, and the slope of the secant here, if I move closer and closer, those slopes become the same slope. Possible? No. Because this one's going to stay -1 and this one's going to stay +1. So it's continuous, but it's not differentiable. And this is one of the easiest examples to show. We also have some, they're called, you probably have seen these in other books, called the cusp. It looks, let me see if I can draw that. Come on. Okay, we'll draw it over here. It looks, that's a very bad example. Let's try that one more time. Looks like that. Where if you take a line and make it tangent to this, and I keep moving it closer and closer to this point, actually, it becomes very vertical. What do you know about the slope of a vertical line? Not 0. 0 is horizontal. Yeah, it becomes, it's undefined because we're dividing by 0. And so it's actually, these become very, very negative. And if we come here, these become very, very positive because they're going to become very positive, very straight up. And so we end up again the same thing. It's continuous, but it's not differentiable at this point C. Okay. Well, some other things that we look at are piecewise defined functions. Now, I don't know how many of you have ever tried to do a piecewise defined function on an 84. It's a little easier with the new operating system they have for 84s, but it's still not as nice as it is on here. We'll come back and pick this up just briefly on Thursday, but I want to show you how to do this, and then if you're interested, you can go through and do this. I'm going to let's go in and pick up another graph page. Remember, we've already used up F1 and F2, so unless I do a new problem, you should be on F3. There is a, and it depends on which model you have. Here is a symbols palette. Let me make sure about this. Yeah, symbols palette. Yeah, there we go, on that key. If you're on the gray one, though, if you look on the control on multiplication, you get to the same thing. Control on multiplication. There's a symbols palette here. And what we want is, and then in the top row, you've got a couple of things you could use. You've got one that has only 2 lines to it, only 2 pieces to it, and you've got one that has 3. If you have more than 2 pieces, you're going to, this one you can use, I don't know how many, 50 or so pieces to a function if you wanted to do that. If you only have 2, you don't have to go to quite the instructions of select the number. So go to the first row and enter that. And if you're on the note page, you'll know that we've got a, let me see if I'll get it here for us again. We've got this function. It's in 2 pieces. And, the first piece is going to be cubing that binomial, but only good for values that are 1 less than or equal to 1. And the second piece is taking that binomial and squaring it, but it's only good for pieces greater than 1. Some of you are working ahead. That means that you know what to do already. So we'll get caught up with you. X minus 1. And I'm going to cube that piece. Tab to get over to that, and you have X, and then we have, let's see, on the gray model, if you go to, see the booklet over here, can you see where I'm circling? the booklet. And if you do control on the book, you've got all those symbols that you're going to need, like less than or equal to and so forth. If you're on the black model, it's a little easier. You have a button right over here on the equals that gives you some of the same things. Okay, so we want this to be less than or equal to, so put the cursor there and press enter. So we want x less than or equal to 1, and then just tab, and the next one is the same binomial, x minus 1, but now we're just going to square it, and then tab, and we're going to say x, and if you're on the black model again, all we have to do is, actually you have to do control on the equals, and it brings up a little palette that we need, and this is going to be greater than 1. Okay, that's all we type it as if we're writing it, and then press enter, and we might have to look at our window a little better, but this piece, it looks almost as if it's continuous here, but this piece of it is the cubic model, and this piece is the quadratic model. So they're not it's not a cubic equation totally there. Okay, what we're going to do then with this, and we'll say the most of the work here, is to find the derivative if it exists. Now let's just talk about what needs to be done. The derivative will only be possible if the function is continuous. Question number 1, is the function continuous? Now, as we talked about in 1.6, these functions, this is a polynomial function. When we square the binomial and cube them, they're just polynomial functions. What do you know about the continuity of polynomial functions? Continuous everywhere, okay? So the only place that this function, this two-piece function, could fail to be continuous is where? Yeah, at the point where they meet. And so we need to determine what's the output when the input is 1, and is it the same output when the input is 1 down here? Now, that doesn't take a whole lot to figure out, does it? If you put 1 up here, 1 minus 1 is 0, 0 cubed is 0. If you put 1 down here, 1 minus 1 is 0, 0 squared is 0. Is the function continuous? Well, obviously they share the same point, and because they're polynomial, we don't have to go through all the other pieces of the continuity. But, so yes, it is continuous. Now the question is, does the derivative exist there? Now, keep in mind, this statement doesn't say that just because it's continuous, that the derivative exists. It doesn't say that. This one says that if the derivative exists, we know it is continuous, but nothing goes the other direction on here. So we need to determine the derivative at 1. Now the derivative is going to be, if I take the derivative as we approach in this direction, remember what limits do, you have to come up from both directions. So if I take the limit as we come up to 1 from the less than 1 side, and find the derivative there, and then find the derivative as we come from the greater than 1 side, and they are the same thing, then we know that the derivative, because we're looking at secant lines, we're looking at the slopes of the secant lines as we get into that. Okay. Hopefully we'll get the projector working better, and we'll do that. Those of you who need to come see me, don't forget, 11 to 12:30, and okay.